Yes.
Good evening, everybody. Welcome to IIT's Gate classes. In this section, we'll be dealing with Gate 2000 flight mechanics problems. In flight mechanics syllabus, this time we got 1 mark question 4 and 2 mark question 4. Total of 12 marks has been asked. We'll go to question number 70. A ideal glider has drag coefficient given by CD equal to CD0 plus CDI, where CDI equal to KCL square is the induced drag coefficient. CL is the lift coefficient and K is the constant. For maximum range of a glider, the ratio of CD0 by CDI is option A 1, option B 1 by 3, option C 3, option D 3 by 2. They have told that it is a glider. So for gliding flight, we know that tan gamma equal to h by range, that is equal to 1 by L by D. They have asked for maximum range condition. For maximum range, L by D is max. L by D max corresponds to drag minimum condition. Drag minimum condition is nothing but CD0 equal to CDI. So the ratio of CD0 by CDI, if you take it, it is equal to 1. So option A is the correct answer. Option A is the correct answer. Next. Gate 2023, question number 19. For a longitudinal stability, for longitudinal statically stable aircraft, which of the following conditions represents relation between lift coefficient, relationship between coefficient of pitching moment about the center of gravity CMCG and absolute angle of attack alpha A. If you see the note, they are given it as nose up moment is positive. If you see option D, we know that for longitudinally stable aircraft, there are two conditions for longitudinally stable aircraft and to be in equilibrium. These two conditions has to be satisfied. 1, Cm0 should be greater than 0 in order to trim at positive angle of attack. Second one is dou Cm by dou alpha should be less than 0 in order to bring back to stability, in order to bring back to equilibrium, original equilibrium condition. Okay. For the aircraft to be longitudinally stable, Cm0 should be greater than 0 and dou Cm by dou alpha should be less than 0. So these two conditions are only satisfied in option D, because here Cm0, Cm at 0 angle of attack is Cm0 is positive and the slope is negative. Dou Cm by dou alpha is less than 0. So option B is the correct answer. If you see the option B, dou Cm by dou alpha is less than 0, that is satisfied, but Cm0 is negative. That means it cannot trim at positive angle. That means it cannot come back to equilibrium. If you see this one, option A, Cm0 is greater than 0, but dou Cm by dou alpha is positive. So it is not coming back to equilibrium at all. If you see here, Cm0 is also negative and dou Cm by dou alpha is also positive. So all these options are wrong. Only option D is the correct answer. Next. Question number 23. Consider the 4 basic symmetrical flight loading conditions corresponding to corners of a typical VM diagram. For one of the flight loading conditions, it is observed that compressive bending stress have a maximum value in the bottom half region. See the figure of the wing cross section, and the tensile bending stress are maximum in the upper forward section of the wing cross section. For the preceding observation, select the corresponding flight loading condition from the option given. They are given in the figure where we have to find out what is it. The corresponding condition is option A, positive high angle of attack. Option B, positive low angle of attack. Option C, negative high angle of attack. Option D, negative low angle of attack. If you take one condition, first we'll take positive high angle of attack. When you are at positive high angle of attack, this is positive high angle of attack. Okay. Now you are at an high angle alpha. Now what happens? The center of pressure region will be moved forward, so there will be a lift acting about this point. Now what happens when there is a center of pressure point is acting forward? What happens? This will take CG will be somewhere here. This will compress the upper region. The lower region will experience a tensile force. Okay. The lower region will experience a tensile force. So this option is wrong because they want compressive bending stress at the maximum value in the bottom half region, and in the upper half region you have to have a tensile force, tensile maximum bending stress. Okay, so this option is wrong. If you keep it positive low angle of attack also, the same thing will happen. So this option is also wrong. But if you see at negative high angle of attack, what happens is the negative high angle of attack, when first we will go to negative low angle of attack. If we even at negative low angle of attack, let us assume most of the aircraft will have even lift. If you see CL versus alpha curve, it will be like this. That means even at negative low angle of attack, you still experience positive lift. So that means there will be only compression, that is compression on the upper forward side, and there will be tension on bottom off side. But if you see the negative high angle of attack, okay, this is negative high angle of attack. So what happens is when there is a negative high angle of attack, there will be negative lift. That means in the forward region, you will be experiencing a tensile force, because when it is having a negative lift, that is, there is a negative pressure distribution. The pressure distribution here, it will be like this. The pressure distribution will be like this. So what happens? It makes the upper half region to be undergoing a expansion. That means there is a tensile force. If you see the rear regions, there will be also lift. There will be small amount of compression. So this region, what happens? There will be ensuring that there will be a tensile force on the bottom region. So when it is about CG, if you see somewhere here, this will undergo a tensile force. This will undergo a compressive force. This will undergo a tensile force. Okay. Okay. The figure is representative. There will be a small amount of positive lift, positive pressure. There will be large amount of negative pressure in this region. Combined, you will experience a downward force only. That what happens? That will squeeze it further. Thereby, you will be experiencing a bottom of region. You will be experiencing a compressive force. So I'll read this figure again. See like this. This is the negative angle of attack. Now, what happens? Since there is a negative pressure here, there will be a suction pressure here. Here also a large negative pressure will be happening. So towards center point, if you see, that is towards CG, somewhere if you see, this upper half region will experience an expansion. But if you see that bottom point where you have wanted, there you will be experiencing this region you will be experiencing a compression. So the only option correct is option C. Next. Question number 32. An airplane weighing 40 kilonewton, is landing on a horizontal runway. When it is landing on a horizontal runway, during which it is retarded by a arresting cable mechanism. The tension in the arresting cable at a given instant, as shown in the figure, is 100 kilonewton. Assuming that the thrust from the engine continues to balance airplane drag, the magnitude of horizontal load factor is dash. If you see, the aircraft is like this. It is landing on an horizontal runway, and there is a tension cable. There is a tension of. If you see this, what happens is the aircraft is landing at an angle 10 degree. First of all, if there can be two assumptions. One is aircraft has already landed. Other one is aircraft is landing at an angle 10 degree. That is rearward angle. That is the rear wheel touches first, then the front wheel touches. So it is at an angle 10 degree. So load factor N is nothing but lift by weight, which is equal to cos gamma. That is lift equal to W cos gamma is the flight. So lift by weight is nothing but cos gamma. So if you put cos 10 degree, then the value of load factor we are getting is 0.9848. They asked us in the integer, round off to 1 decimal places. If I am rounding off to 1 decimal places, this will approximately equal to 1.0. If you take this way also, it is 1.0. If we assume the aircraft is landed, let us assume the aircraft is already landed. The landed aircraft, what is nothing but, it is nothing but, load factor is nothing but reaction force divided by weight. The reaction force here, when it is balanced on the ground, the reaction force is also weight. So the reaction force, that is already weight is acting. The upward reaction force will be also weight. So it is weight by weight, then also load factor is 1.0. If you consider both the cases also, load factor is 1.0. So the answer is 1. Answer is 1. Remaining all is just for retarding, that is thrust. It is not only balancing your drag, there is an additional drag is given by this arresting cable, so it is can be retarded faster. Okay. Next, question number 40. Consider a general aviation airplane with weight 10 kilonewton and wing platform area of 15 meters square. The drag coefficient of the airplane is given as CD equal to CD naught plus KCL square, with CD naught equal to 0.025 and K equal to 0.05 for a level flight at an altitude where the density is 0.6 kilogram per meter cube and the thrust is 1 kilonewton. The maximum cruise speed is round off to the nearest integer. Option A is 87 meter per second. Option B 30 meter per second. Option C 36 meter per second. Option D 101 meter per second. First, what are the given data? We know that weight is nothing but 10,000 Newton because 10 kilonewton is nothing but 10,000 Newton. Wing area is 15 meters square. CD is nothing but 0.025 plus 0.05 CL square because K is given as 0.05, CD naught is given as 0.025. Substituting that in CD equation, we get CD as 0.025 plus 0.05 CL square. Then density is 0.6 kilogram per meter cube. The thrust is 1 kilonewton, which is nothing but 1000 Newton. Okay. In order to find maximum velocity, we know that thrust equal to drag, that is equal to K1 into V square plus K2 divided by V square. We know that K1 is nothing but CD naught into half rho s. So we know CD naught is 0.025, density is 0.6, wing area is 15 meters square. So we get CD naught to the K1 to be equal to 0.1125. So it is 0.1125 V square. Thrust is nothing but 1000 Newton plus K2. K2 is nothing but 0.05 into K into W square by half rho s is K2, where K is nothing but 0.05, W is nothing but 10,000 Newton, 10,000 the whole square by half, density is 0.6, wing area is 50. Substituting that, I get K2 as 1111. It is 71.111. So substitute that by V square. Now I take V square on the other side. I take common factor as V square. So I get it as, I get that equation as 1000 V square equal to 0.1125 V power 4 plus 1111.111. Okay. If I take this also on the other side, that is 1000 V square also on the other side, my equation has become 0.1125 V power 4 minus 1000 V square plus 1111.111 equal to 0. So if I take x equal to V square, this equation will become 0.1125 into x square minus 1000 into x plus 71.111 equal to 0. In this, if I have to solve this problem, we can take A as equal to 0.1125, B as equal to minus 1000, C as equal to, okay. Now, how to solve this problem? X equal to minus b plus or minus root of b square minus 4ac by 2a. By 2a. They have asked the maximum cruise speed. So only the positive value if I take, that is more than enough. That will give you the maximum value. So when we will get maximum value, the maximum value we will get it as when there is a plus sign. Okay. So substituting that, we get b is nothing but 1000 minus 1000. So minus into minus will become plus 1000 into root of minus 1000 the whole square minus 4 into a is 0.1125, c is nothing but this one by 2a. A is 0.1125. So x max value we get it as 7587.14125. Okay. X max is nothing but v square. So it is v max square. It is nothing but v max square. So from that we get v max equal to root of this answer. That is equal to 87.104 meter per second. The nearest answer in this option is option A. So option A is the correct answer. Okay. Next. Question number 45. Consider the International Standard Atmosphere ISA with H being geopotential altitude in kilometer and dt by dH being the temperature gradient in Kelvin per meter. Which of the following combinations of H, dt by dH is R as per ISA? Option A, 7 km at 7 kilometer altitude, the lapse rate dt by dH is called as lapse rate. At 7 kilometer geopotential altitude, the lapse rate is minus 6.5 into 10 power minus 3. Option B, 9 kilometer geopotential altitude, the lapse rate is 4 into 10 power minus 3 Kelvin per meter. Option C, at 15 kilometer geopotential altitude, 0 is the lapse rate. Option D, at 35 kilometer altitude, the lapse rate is 3 into 10 power minus 3 Kelvin per meter. We know that ISA is like this, altitude versus temperature. So the dt by dH value at from 0 to 11 kilometer altitude is minus 6.5 into 10 power minus 3 Kelvin per meter. So up to 11 kilometer altitude, the lapse rate remains minus 6.5 into 10 power minus 3, the rate at which temperature decreases with respect to altitude. So if you see this option, option A, that at 7 kilometer altitude, the lapse rate is minus 6.5 into 10 power minus 3. So option A is correct. From 0 to 11 kilometer altitude, we know that the lapse rate is minus 6.5 into 10 power minus 3 Kelvin per meter. That means at 9 kilometer altitude also, the lapse rate is minus 6.5 into 10 power minus 3. So option B is wrong. If we take option C, from 11 to 25 kilometer altitude, the temperature remains constant. So the lapse rate dt by dH value becomes 0 from 11 to 25 kilometer. That means at 15 kilometer altitude, the lapse rate is 0. So option C is also correct. Now if you see, they asked in 35 kilometer. From 25 to 47 kilometer altitude, the lapse rate is 3 into 10 power minus 3 Kelvin per meter. So anywhere between 25 to 47 kilometer, the lapse rate should be remaining 3 into 10 power minus 3 Kelvin per meter. So they given at 35 kilometers, that means 35 kilometer also, the lapse rate is 3 into 10 power minus 3 Kelvin per meter only. So option D is also correct. So the correct answer for question number 45 is option A, C, and D. All these three options are correct. Only option it is wrong is option B. Okay. Next. Question number 59. An airplane with wing platform area 20 meters square and weight 8 kilonewton is flying straight and level with a speed of 100 meters per second. The total drag coefficient is 0.026. Air density is 0.7 kilogram per meter cube. The thrust required to introduce steady level climbing uh, angle of zero point 0.1 radians is dash. Okay. The two equations constitute for level flight. The climbing flight is lift equal to W cos gamma. Thrust is equal to drag plus W sin gamma. Because during climbing flight is like this. Lift will be always perpendicular to the free stream velocity. The free stream velocity is like this. And this is your gamma angle. Weight is perpendicularly downward. Drag will be perpendicular to lift. So this also will be gamma. Now if you resolve this equation, if I normal to the lift equal to W cos gamma towards the angle, and there is one more force called as thrust equal to drag plus W sin gamma. So we have to find out what is thrust. Thrust equal to drag plus W sin gamma. We know drag is nothing but CD into half rho V square S plus W sin gamma. CD is already given. Total drag coefficient is 0.026 into half. Density given it as 0.7 kilogram per meter cube. So 0.7 kilogram per meter into 100 is the velocity, 100 square, into wing area is 20 meters square. So wing area is 20 meters square. Plus weight of the aircraft is 8 kilonewton. That means 8,000 newton into sine gamma. Gamma is in radian. If I have to convert into degree, I can multiply it by 180 by pi. Then solve this. Okay. If I have to convert into degree. Otherwise, we can use in calculator radian and put sine 0.1 itself. If calculator in degree it is there, we can use degree itself. Then, if you want to solve this, when solving this, I get 1820 plus this one, I get it as 798.667. So answer I'm getting it at 2618.667. They asked us to round off to nearest integer. The nearest integer is 2619 because if I round off, it will become 9. 2619 Newton. So the answer is 2619. Okay. Next. Question number 60. The maximum permissible load factor and maximum lift coefficient for an airplane is 7 and 2. The wing loading of 6,500 Newton per meter square. Air density is 1.23 kilogram per meter cube. The speed yielding the highest possible turn rate is in the vertical plane is dash meter per second. The highest possible turn rate occurs at a velocity called as corner velocity, which is nothing but 2 into n max into W by rho into S into CL max. We know that N max is equal to 7, CL max equal to 2, wing loading W by S equal to 6,500 Newton per meter square. Wing loading is nothing but weight divided by wing area. So it is 6,500 Newton per meter square. Density, they are given it as 1.23 kilogram per meter cube. And they asked us what is the speed. 2 into N max into W by S by rho into CL max. Substituting the values is 2 into 7 is the load factor. Wing loading is 6,500 divided by density is 1.23 and CL max is 2. Substituting that, I get that velocity as 192.333 meter per second. Round off to nearest integer, that means it is 192 meters per second. If you have any doubt, you can ask. Otherwise, the section is over. Okay. Thank you. Thank you.
You are currently the only person in this conference.